Very good, thank you. Very good, thank you.
Baik, selamat pagi Bapak Ibu, rekan-rekan engineer yang saya hormati. Selamat bergabung dalam acara webinar hari ini. Salam sehat selalu tentunya untuk kita semua dan mudah-mudahan kita semua selalu bersemangat. Kemudian bersama saya lagi sebagai moderator, kita akan memulai webinar seri kedua ya dengan tema pengaruh angin terhadap bangunan gedung dan juga struktur bentang panjang. Nah, webinar bagian pertama yang dilangsungkan 2 minggu lalu itu berhubungan dengan Wind Tunnel Testing untuk bangunan gedung tinggi. Dan mudah-mudahan kita sudah bisa mendapat manfaat dari webinar tersebut. Webinar lanjutan kali ini akan membahas tinjauan pengaruh angin untuk struktur atap stadium dan struktur atap bentang panjang lainnya. Saya rasa ini merupakan topik yang penting dan menarik. Mudah-mudahan seri webinar ini juga bisa menjadi pembelajaran yang bermanfaat bagi kita semua. Jadi jangan lupa memanfaatkan kesempatan untuk menyampaikan pertanyaan yang dinilai bisa memberi manfaat bagi peserta lain melalui kolom Q&A. Selanjutnya, izinkan saya memperkenalkan pembicara kita hari ini, Dr. Nicholas Truong. Dr. Nicholas is a professional engineer with over 15 years of consulting, research and development experience in the field of fluid dynamics and wind engineering. Dr. Nicholas is responsible for WindTech's ongoing innovation, research and development program to maintain WindTech's position as a global leader in the field of wind engineering. Okay, so without any further delay, let us give our full attention to Dr. Nicholas Truong. And join me in welcoming Dr. Nicholas.
Well, thank you very much. I will now share the screen. Okay, thank you very much for that introduction. As discussed, my talk today is on advanced techniques for the study of wind loads on stadiums and long-span roofs and structures. So the talk will consist of 5 parts. So I'll discuss the pressures on the roofs. I'll spend some time looking at wind tunnel testing methods, and then I'll go on to talk about, in particular, the load correlation response method, and then I'll go through some case studies of roofs and some other interesting structures. All right, let's go. And as it indicates, sorry, that's the slide. Okay. Okay, so pressures on roof structures. So the main thing about roof structures is they can be quite complicated in terms of the pressure distribution. And one thing is that the roof pressures will fluctuate over time. And this is really the reason that we need to spend a lot of time doing specialized testing using the wind tunnel. So for example, we can see here that at the first point, we have a high negative load on the leading edge. And at some other point, there's a larger negative load at the top of the roof here and slightly lower pressures here compared to the first case. But in all of these cases, we've got a strong positive pressure on the front and a strong negative pressure on the back. But as you can see that the pressure distribution on the roof can vary. And it's because of this fluctuating load that we need to use special techniques in order to analyze the loads. Sorry, this is just what I was saying there. So let me move this. So what makes a long span roof different? Okay, so the key differences are the properties of the structure, the applied wind load, and the structural response. So in this example here, I've got a stadium that we tested in Australia. Now this is the wind tunnel model of the stadium, and this here is after the stadium was built. As you can see, this isn't the longest stadium roof. However, it's got some interesting properties, and that's why I've chosen to look at it. So in particular, for this roof, it's only got a single main centrally supported structure here. So you can see here, there's 2 pylons, and that's linked up to this truss structure across the top that supports the roof. So unusually, for a stadium. There's no back connection here. And so what this means is that the structural response of this building is quite different because we don't have a typical cantilevered roof. And in particular, for this structure, there was prior to our involvement in the testing, there was a small failure, and the failure occurred at one of these joints here. Now, this happened because the original designer of this building used a standard approach, and the standard approach doesn't include some of these interesting structural responses. Okay. So the applied wind load. So one key point to understand about wind loading is that we need to think about the correlation of the natural wind flow. So peak gusts are not correlated. So what we can see here is that if we have 2 points, point A and point B, and we can look at this this example here of the wind speeds at the 2 points, we see that the wind speed at point A and the peak wind speed at point B don't happen at the same time. So when we design the structures, we need to try and account for the fact that there is a lack of correlation of the wind speeds. So in this example here, we can see that if we use the gust envelope, which is the blue line to design the structure, we would design the structure for about 43 meters per second in this example. Now, the 43 meters per second represents the peak wind speed that occurs along, say, the bridge in this case. Now, if we then account for the lack of correlation, we can come up with some different wind speed distributions. So I've given 2 different distributions here. And this is based on an exponential decay in the correlation length. So what we see here is that when the peak gust occurs at this point, we can, using some statistical methods, we can estimate what the most likely wind speeds are further away. And so this will give a different wind speed distribution. And that means that your overall structure will experience overall a lower load. And this is one of the things that we can pick up using the wind tunnel testing. Okay. Another important feature of long span roofs is to do with the correlation of building induced pressures. So here in this example, we're going to look at this interesting roof, which is for a proposed airport. And you can see we're going to focus on 3 regions, the region on the left, the region in the middle, and the region on the end, and the wind's coming in this direction. So as it's a roof, we'd expect there's significant uplift pressure, and because this has a slight overhang, you'll get a positive pressure underneath and a negative pressure on the top. So there are multiple different pressure scenarios that could occur. So you may have a scenario where there's a peak load on the left, and that's low in the middle and on the right. You might have a scenario where the peak loading is the other way around. And you may have a loading where it's uniform across the middle. Now, the importance of these 3 different load patterns is depending on what part of the structure you're trying to design, it depends on which of these load patterns is the most important. So just going back to the beginning, if you're designing this end section here, which is quite a critical section, I mean, these corners are always subject to high wind load, this distribution would be the most important to help you design the members in this area. In the same way, this pressure distribution here is the most important to design the beams in this area. However, if you're interested in the overall load for some member that might be running the whole length, or you have supporting structure underneath, then you need to consider what the overall maximum load is. And so this is why we need to consider sometimes multiple different pressure distributions. The other reason that long span structures are different to conventional structures is that you can have quite complicated mode shapes. So in these 2 examples here, we've got 2 stadium roofs. So this is a stadium in China, and the seating is underneath it, and this is obviously the roof here. And you can see in this mode that there's positive displacement here and there's a negative displacement down here. So we need to try and incorporate this interesting mode shape into our analysis. This example here is a stadium in India, and you can see that it has this sort of wiggle in the mode shape due to the vibration. So this also needs to try and be captured by the analysis technique. So I'll briefly talk about some wind tunnel testing facilities. So depending, I'm not sure how much you know about wind tunnel testing, but we Windtech has 3 wind tunnels and they're all very similar, and it's a standard open jet wind tunnel. So we have a large fan at one end. We have some devices in here to reduce the turbulence in the flow. And then we start to create the atmospheric boundary layer. And we can rate the atmospheric boundary layer by using these spires and tripboards. It flows along this section here, which is roughness elements, and they represent, for example, like small houses. And then we have the model on a turntable in here. So you can see here again, this is a stadium development, and you've got the roughness elements and you've got the tripboards. So that's quite relevant to what we're doing. And some other study that we might do is this study here. This is a topography study. So if you have a stadium or that's in an area with a lot of hills, we might do a topography study to start with, and then we would figure out the effect of the mountains or the other topography on your site. So in wind tunnel modeling, we use a scale model. So typically we would use a scale model in the order of 1 to 300 to 1 to 400. And that's normally sufficiently large to have a good Reynolds number. All of our models are using computer-aided design, and we use 3D printing. So this is quite a complicated model here that's been 3D printed, and that allows us to get all the shapes in and all the different curves. And then typically you would include a radius of between 300 and 500 meters around the development of all of the surrounding buildings. One question that quite often comes up is a comparison between the aeroelastic method and the Lrc method. So the traditional approach is the aeroelastic method. This is an example here. And in this method, the model moves. So the idea is that you build a stadium roof, for example, this one here, and you try and replicate the actual mode shapes and scaled masses and scaled damping of the roof. Now, this is a very complicated process because it requires a lot of engineering work to actually design the model correctly. And then what happens is you put the model in the wind tunnel, you take some measurements of the displacements of the roof, and then you translate that to the real model, the real building. Whereas what I'm going to talk about today is a load response correlation method. In that method, we use a static model, like you can see here, and it doesn't move. But what we do is we measure the applied wind load. And the applied wind load is measured using all these pressure sensors, and you can see they're underneath these dots, and they're connected to these pressure tubes, which are then connected underneath the wind tunnel. And using this method, we mathematically account for the movement. So here are some other points about the Lrc, which I've covered. It can be expensive and time consuming for it to take place. It can be difficult to build a model. But importantly, if the structural properties change significantly, you have to rebuild and then retest the model. So if you want to have an iterative design process, it's very difficult to do that with an aeroelastic model. With the Lrc model, or direct load effects method, we overcome some of those problems. Now, one of the reasons that this method wasn't used historically was it's far more intensive with the computer processing, but now obviously that's a lot easier than it used to be. It also accurately accounts for the lack of correlation of the peak pressures, which we'll discuss. It does need a little bit more information from the structural engineer in terms of some influence coefficients. So this is a little bit more work in the beginning. However, the real difference with this method is it provides a set of equivalent static point loads. So instead of giving just one deflection or a couple of deflections of the roof, in this method you will receive a series of pressure distributions. So you might receive 20 or 30 or 50 pressure distributions, and these pressure distributions are designed to maximize the pressure or the response at different areas. So in this example up here, you might have a pressure distribution which maximizes the deflection of the roof at here, and you might have another pressure distribution which maximizes the drag acting in this direction. And they're all separate pressure distributions, and they allow you to accurately design all the different members instead of just using a single displacement or something like that. Okay, so I'm going to go into a little bit more depth about the load response correlation method. So the key to the load response correlation method is this equation here. So what it's saying is that if you apply a pressure at a given point and you multiply it by an influence, you'll get a response. So that's all that's basically the half. And so the response to the structure can either be a displacement, a stress, or a bending moment, or it can be anything else that you can measure in a structural model. And so every time you apply a pressure to your model, there will be a small change. And we capture that change by using influence coefficients. And as I said, you assume that there's a linear relationship between them, and then you just sum over all of the different pressures. And I'll explain how we do that. Okay, so the first step is to create a link between the applied pressure, which is the load in the load correlation method, and the response. And to do that, we use an influence coefficient, and I'll show you how we do that. So in this example here, we have a simple roof structure. Sorry, we have a simple roof structure here. And what I've done is, sorry about that, I've divided it here into six parts. Oh, it's playing. Okay. I'll just stop this. Sorry. So you can see here, I've got a roof here and it's in 6 parts. 1, 2, 3, 4, 5, 6. And the interest in this part is the deflection. So that's the deflection here. So what we're saying here is that we have a response, a pressure, and an influence. So to start with, we look at point 1 and we say, what happens if I apply a pressure at point 1? And then what is that effect on the deflection there? So going through this, you'll see what we do is we apply a unit pressure here, and then in the member of interest here, we measure a response. And we go through that slowly, and we have all of these series of responses for the different I values. Okay. And at the, let's go back to the full mode. And at the end of that, we can use these measured influences together with an assumed pressure distribution to calculate a response. So in this example, I've looked at a standard here for a domed roof, and you can see that typically you'd have a positive pressure at the leading edge, you have a strong negative pressure at the top where the flow separates, and then it sort of weakens as you go down the back end of the dome. And so I've just looked at that and estimated the pressure distribution, and you can see there's it's stronger at the top and a positive at the front, and it sums up to that response. And so that's basically the heart of the method. And this animation really just shows you that again in practice. So all this is showing here is it's looking at the bending moment, and that's the bending moment value there. And what this animation is showing is that as the different pressure distribution moves around, you get different values of the bending moment. And these lines here represent the peak values. So this animation is from Michael Kaspersky, who came up with the method. And in the second part of the animation, we're looking at the same idea again, but we're looking at the bending moment on the back side. Okay, so another method that you can use is called the direct method. So the direct method is quite similar. So the direct method also uses the pressure distribution and the influence coefficient. So once the influence coefficient is determined, if you have the time series of the pressure, just like what we saw before, you can then work out what the response is for every time, and then you can just take the maximum of that R value, the response, to work out what the maximum response is. But the key question then is, which pressure distribution caused this response value. Is it just the pressure distribution which happens to occur at the same time? Or what happens if you have a response that is 2% less than the maximum, but has a completely different pressure distribution? How do I account for that? So this is the key difference between the direct method and the LRC method, is the LRC method predicts the statistically most likely pressure distribution to cause the response. And I'll show you this example here. So going back to this example here, you can see we have a response here. Now, I can come up with a different pressure distribution here, in which case I've made a small change to these values here, and if you add them up, you end up with about the same answer. So the key question is, which pressure distribution should I use and why? Because although you'll have the same response in this member, which is good, if I'm going to apply this different pressure distribution to my structure, you may find that there's a different response, say, in the middle section here. So the heart of the LRC method is to determine this pressure distribution. So this is the so-called Lrc equation here. And as I mentioned, the Lrc method was derived by Michael Kaspersky in the early 1990s. And then it was extended by John Holmes to include the resonant response. And it's considered by many to be a landmark event in wind engineering because it's a very simple concept after you go through all the maths to get to this equation. So what it produces is an instantaneous pressure distribution for each load effect. And the pressure distribution is predicted by this equation. So it takes the mean pressure, the peak factor, the standard deviation of the pressure, but importantly, this factor here. So this factor is the correlation between the pressure and the response. So once you know the correlation between the pressure and the response, you can estimate what the load effect, the pressure distribution is. But what it does require is it requires you to measure all the pressures at the same time and work it out. So all the pressure measurements have to be taken simultaneously so that you can work all of this out. So I'll provide you an example of correlation just to give you a bit of a feel for what I'm talking about. So this is this roof that we saw earlier. I'm going to look at the correlation coefficient, which is between some sensors. So this sensor here in the middle and other sensors for two different wind directions. So in here, I have, okay, so we're on the, I should say, we're on the east side here. This is the east side, and this is the west side. And so the west side has a row of taps, and the east side has a row of taps. And these values here represent the correlation. So what we can see here is this is the central tap. So this is the central sensor that we're most interested in. And you can see that it decreases with distance. So what we're saying is that the correlation between the peak pressure here decreases as we go along the backside. And along the two edges. And so the Lrc method captures this effect, and it uses this correlation to determine what the most relevant pressure distribution is. If you go look at the leeward side, what you see is that the pressure distribution is actually quite uniform. So that means that there's actually, for this particular case, not a strong correlation between any of the pressure taps and on the backside with what's happening on the front. Now that's not unexpected because there's actually quite a long distance between them. So what will happen is that you have a peak gust occurring here. You have some sort of structure developing across the roof, and then you may get a stronger negative pressure at the back, but that wouldn't occur at the same time as the pressure on the front. So that lack of correlation can be accounted for using the method, the Lrc method, and any good wind tunnel method. So you can see here again, this is the zero case. So the zero case, as you can see, has a slightly different wind angle. We're coming slightly obliquely. Once again, you have the one in the middle. It's decreasing with distance, and it's uniform on the leeward side. But interestingly, in this case, there's actually an increase in the correlation. although it's still uniform, there's a slight increase in the peak pressures on the backside compared with the front, which is an interesting effect. So this is the kind of thing that we can see in the wind tunnel, and this is why it's important to use these correlation methods. So, so I hope this short example has shown you why we should consider correlation. So I'm going to go and show you now some different examples. So the first example I'm going to show is for this stadium in New Zealand. So this stadium is in the South Island of New Zealand, in Otago, and it was built for the Rugby World Cup. And you can see this building has a bit of topography around it, and it's also got an interesting curved roof. So this is the building in the wind tunnel, and this is the completed building here. So this building has what at the time was quite unusual, which is a PTFE roof, which was clear. So these have become more popular in recent time, but this is one of the early uses of this technology, and it has a series of pillows, what they call pillows, in here. So the idea, I'll just show you the next picture. The idea is that the light can come through the roof and it lets the grass grow. And so you can play the rugby in the not in the rain, but the grass can still grow. So this would be almost impossible to model using the aeroelastic method, because you would have to have modeled the interaction between the structural members and the PTFE. And that would be quite difficult to model at scale. So one issue is that when you make the aeroelastic models is you need to make everything smaller. And one problem, sort of practical issue you have with a lot of wind tunnel models is that it can be quite difficult to make everything small and fit together. So that's one great advantage of the 3D printing, which you can see here. The 3D printing has allowed us to build these intricate structures. So when I first started in wind engineering, we had to build these models by hand, and we would glue these together, little pieces of wood together, to represent this. Now, you can imagine that's quite difficult for this. So that's one advantage of 3D printing. And you can then imagine having to go on to make a complicated aeroelastic model. Okay. So in this example here, you can see that we've divided the structure up into panels. So as I showed in the dome example, everything is based on panels. So each panel has to have a series of pressure sensors. That's what these are. These dots represent the pressure sensors. So for example, here we use 570 pressure taps, and we have 100 areas. Now it's very important that if you're looking at one of these layouts, that you have more than one sensor, sorry, more than at least 2 sensors, if not 3 or 4 sensors per panel, so that each of the pressures truly represent the pressure on the panel. If you only have one pressure sensor, for example, in the middle here and the middle here, the pressure for that, it only represents that single location, not the panel. So that's why it's very important that you have multiple taps per panel. We also have sensors on the back side, and that's what these X's represent. So we could measure the internal pressure as well. And that's one other advantage of using a static model. So in this case, there were openings, and obviously the grass needs ventilation. So there were openings all along here, all through here, and there's also openings underneath to allow the fresh air to move through this. So if you wanted to do this with a aeroelastic model or another physical model, you would need to adjust the internal volume of the model. And to do that, what you typically do is that you build another box actually underneath the model, and we expand the volume. So what's mathematically demonstrated is that wind tunnel models won't, wind tunnel models need to have an expanded volume compared to full scale models to correctly capture the internal pressure fluctuations. Whereas when we do this method using the pressure sensors, we measure all of the wind speed, the pressures at all these locations, and then we mathematically calculate the internal pressures. And so for large roofs, internal pressures are very important. I haven't included it here, but we've done a lot of work with aircraft hangars, and as you probably know, aircraft hangars have large doors to let the planes in. And so you'll get very different pressure distributions when the doors for a large hangar is open compared to when it's shut. And that's something that we can capture. So moving forward with this, I'll show you an example here of what we would do. So typically the structural engineer has a detailed model here in ETABS or SAP or something of all the different elements. And in this example, they've selected 4 important load effects. So you can see in this load effect here, you've got an axial force of a member here, another axial force down here, a displacement at the top, and also a reaction at the bottom, of the base reaction. So this is quite a typical distribution. The deflections, the rooftop deflections are always important. Sometimes you may also have a deflection on some of the edges, depending on how your structure is designed. The stresses in critical members, I mean, most designers will know which particular members they're most worried about. Quite often there's shear in the joints that you might be interested in. And then finally, there's the base reactions at the base of the supporting structure. So this is all very, very typical. Now, for this particular stadium, they were concerned about the resonant response. So the basic LRC method, as derived by Michael Kaspersky, does not include the resonant response. The subsequent work by John Holmes then added in the resonant response. And so this allows for the amplification of the structure to amplify the dynamic response. Now, we would typically only recommend performing that if the first mode is less than 0.8 hertz. Now, for this example, we considered these 3 modes. So there's 0.7, 0.76, and 0.89 hertz. If there'd only been one mode, perhaps if that was the first mode, perhaps we wouldn't have included it. But once you do one, you may as well include 3 or 4. It's the same amount of work, and it'll capture all of those effects. And so what we found was that the combined effect of the first 3 modes had the maximum of increasing it by 10%. And that's a maximum of 10%. So you can see here in this load effect 3, which is the reaction force of the node, the change that it had. So the background is the dashed line, and then the solid line is the resonant response. So the background response is the response of the structure to the mean wind speed, so that's the mean is here, as well as the slowly varying pressure fluctuations. So you can see that's what has occurred here. And then the resonant response is just added on. So the resonance response is just this small amount here. This is another example where you can once again see the resonant response. And so this is fairly typical for critical members, so that you might have a 5 or 10% increase. Okay, so this is an important graph, although it's a little bit complicated. So what the graph shows is along the x-axis, they're all the panels. And so that's all of those 107 panels. And on the y-axis, we have the pressure. So the red line here represents the peak positive and the peak negative pressures that were measured at any point on the panels. However, all the other lines underneath it represent the load cases that were derived using the LRC method. And so what you can see here is that this blue pressure distribution, for example, is always less than the red line. So by using the LRC method, and by considering the correlation, which I talked about earlier, and by then also then bringing in all the influence coefficient information, we're able to determine these pressure distributions. So once these pressure distributions are determined, it turns out that the maximum load effect for A occurs without having to reach these maximum pressures on each of the panels. So this really shows you how important it is to look at the correlation effect. So typically, if we don't look at the correlation effect, the method that we use, and there's nothing, it's a perfectly good method, it's just a little bit conservative, is that we would take these pressures, we always take the maximum pressures, and then we combine them to work out a pressure distribution. And you can see that's perfectly safe because it's always greater than the pressure distributions on the inside. The other key point is that for every load effect, there'll be a maximum and a minimum. And so you'll, generally speaking, derive two different pressure distributions, one for the maximum case and one for the minimum case. And so if you, as a designer, have 30 load effects, then you would find that you would have us produce 60 pressure distributions. Okay, so this is the next case study. So this case study is in Nanjing, in China. You can see that's the model in the wind tunnel, and this was the completed structure here. And so this is the one I showed you before with the interesting mode shape. And you can also see, really, this photo really shows you the extent of this fin here. And so this fin obviously radically changes the flow over the top of the stadium. Typically, stadium roofs can be quite tricky to predict the wind distribution anyway, but with something like this here, when the wind comes from this direction, you can imagine how this will funnel some of the wind flow underneath it, and also maybe lift off some wind direction. It will push some of the wind over the top. So you have sort of two counteracting effects occurring. Also, because it's open underneath and it's lifted up, I'm not sure that's particularly clear, there's a slight incline on this roof. So the wind can get underneath it, and it can go under top between the gap, and it can also go over the top. So there's all sorts of funny wind effects occurring just because of this unique architectural geometry. So for this study, we instrumented it with 512 sensors, and we used 64 panels, and the panels covered both the main stadium roof through here, as well as that interesting architectural feature on top. For this one, we also included the resonant effect. As I mentioned earlier, there's a lot of mode shapes, interesting mode shapes occurring with this one here. You've got the, I guess, you've got these two here, and they're moving in the same direction, and these are in the opposite. And then you've got the next case over here where this is going up and down and up and down. So this is like the opposite of this case. And then you have, I guess, a more predictable mode shape when everything's going up at the same time. And then you have the anti-symmetric case when one's going up and one's going down. So these are all, I guess, relatively expected mode shapes, but we really need to account for them. You can also see, interestingly, how closely spaced they are. So these are all within 0.05 hertz of each other. That is actually quite unusual in our experience. Typically, you would see those modes being a little bit more separated. And I would have expected, if we hadn't seen this, that these two first order mode shapes would have had a slightly lower frequency than the second order mode shapes. And that is slightly unusual. So in this case here, we'll just look at the vertical displacement. And interestingly, despite all of what I've said about those interesting mode shapes, for this critical member, the effect of the resonance was actually quite small. And interestingly for this, even though you can see the resonant effect with this dashed line here, it turned out that the because of the effect of the mean response, it didn't really have much of an effect. And what I mean by that is that you can see here the mean response is quite large, and that dominates helps make this load effect here dominate, and this mean response here makes this part dominate. So even though that this resonant response in this section is higher than here, the mean effect has actually sort of pushed it further for the negative displacement, and the same for up here. I think that the largest resonant response is here for that side, and you can see how that's worked together there. So even though we've included the resonant response, in the end, it doesn't actually dominate the response for this structure. Okay, so this is another stadium in India. Now this stadium is a retrofit stadium. So the main bowl of the stadium exists. However, they were expanding it to become the biggest cricket stadium in the world, and they wanted to put this flexible roof on the top. And you can see this roof here. So for a more modern stadium, this is quite typical. You have the tension fabric structure supported by a steel frame, and you have these gaps at the back. This is also quite common, and it's cantilevered out over the top. And because of it's a retrofit, the sail structure sort of self-contained. So we were only interested in working out the pressure distributions on the top side, and you can see here. Let's see what's happened here. So this stadium had some very complicated mode shapes. And so what we can see here with the mode shapes is that there's some small deflections here, but really it's these really odd sort of mode shapes that are occurring all around the building. And so these are just some of the mode shapes that we looked at. As you can imagine, that this sort of wiggling circle effect occurred all around the building. So there's a lot of mode shapes that look very similar. Basically, you can see there's a large deflection here for this mode shape and a large deflection here for this mode shape. This kind of pattern repeated itself all around the building. So what that showed, though, so the effect of that later on was that because each of these mode shapes is actually quite isolated to one region, when we looked at the resonant effect, we could see that effect. So that's actually something quite interesting. There's a link between the mode shape and then the resonant effect about how localized it was. So I'll show you this example here. So this example here is the members in this area here. And once again, just to go back again to this here, every area, I mean, I'm not sure if it actually was this area, but you can see localized to every area, there was a large displacement occurring there. So what this is shown later on is that when we've included the resonant effect, there's actually a very large effect for when the wind comes in that direction, in this kind of quadrant from the north. You can see there's a large resonant effect, and that's because the dark line is so much higher than the open dot, which doesn't include the resonant effect. And once again, here on the south side, you see the same thing again. You can see the strong resonant effect here. So in this case, it was very important that we did this extra analysis to include those extra loads. However, when we look at the total structure, this is where it becomes interesting. Because of what I said in the beginning about the mode shapes being very isolated to particular areas of the structure, when we looked at the total uplift in this case, you can see that the resonant contribution is negligible. So this is the uplift, right? So this is the total uplift on the whole, all of the roof. Now that's because when you did have that resonant effect, it was always localized. So when you consider the whole roof, you don't get that strong effect. and also because of the correlation. So when we consider the resonant effect, we're also including the correlation, because it's the correlated forces that occur at the areas where there is a strong mode shape deflection or strong sign of the strong magnitude of the mode shape that have to work together. So I might just say that again. So for people who are familiar with how the modal analysis works in wind engineering, we calculate the generalized force, and the generalized force is a combination of the mode shape at a location and the force acting at that location. So when you get a strong correlation of force of wind and mode shape, you'll get a strong generalized force, which leads into a strong resonant response. And that's why you see for these, just going back, that's why you see these here, because you will get a strong correlation in this area together with that mode shape value, large mode shape value, whereas for the lift value, you won't have that. So they're sort of all working together. And that's the same with the shear. You can see the shear has basically very little interaction. Okay, and so just finally, I'm going to look at some other LRC examples. So this is something that we did some time ago, but it's probably one of the most interesting structures that we worked on. So this was for the Doha Asian Games, and what it is a light, and so a flame. So there's a flame here, and it's obviously horizontal when it's burning, and you have all of these extra discs. What do they call it? Circles that move around it. So you can see them here. These are all the different things, and they move around. Now, the rings themselves can be in different positions. So you can have them in the basic position like this, and they're all together. And then as it moves around, it makes a pattern. And so they're constantly moving, and you have the fire, and it looks really good. So this was built for the Doha Games, but because it was such a feature, it's actually been moved outside. So it's not where it was, it's in the park nearby as a real feature. Now, in terms of modeling it, it was quite challenging. So we had to model the rings in different positions. So there's the so-called construction mode, and that's when obviously the flame isn't on and it's all flat. And so that's the way it was built, and that's the way it was put together. And then there was the rings collapsed operation mode, and that's where the rings return to. And obviously, it's flat with the fire going on, but the rings are like this. And then when it's in operation. So when it's in operation, we just selected, in consultation with the designer, some representative positions of the rings so that we could look at them. Now, this was a very difficult job to instrument, as you can imagine. So what we did is we put pressure sensors into the 3D model. So we actually embedded, well, I said that here we've embedded the pressure tubes, but a better way of thinking about this is that when we 3D printed the model, the tubes are actually built in. So there is actually a very small channel running through all of the rings, which are then connected up to the pressure tubes at the bottom. So this is very difficult to do, and it requires a special printing process to get this done. Now, one of the reasons that the designer was interested in this is that to have the effect, the correct effect, the rings need to be quite close together. And so this was the displacement required, was 0.05 meters. Now, in that case, if there's a strong wind load, there's a possibility that it might move the rings around. So obviously there's a lot of vibration going on. There's lots of different forces going on, and they wanted to make sure that if the worst happened and there was a wind gust at a certain point and the thing was moving in a certain way, how much room have they got for the whole scene to make sure that it didn't start scraping when the rings were moving. So what you can see here is I've zoomed in on the edge here, and what we're looking at is the displacement, the crosswise displacement in here. So you can see that there's a pressure sensors are located down here, and we have the displacements at in the 3 different configurations. So ring D is the outside ring, if I remember rightly. Yeah, that's D. Yeah, that's the outside ring. And then in the construction mode, in the closed mode, and in the operational mode, we calculated the pressure. We measured the pressures, and then we went on to calculate what the displacements are. And so that effect goes on for several different rings. And the other thing they were interested in is the torque. So the torque, the rotational moment of this here. So obviously that's quite tricky to estimate given the shape, and especially also given, I mean, these the rings in a very unusual situation about how much twisting the mast would be susceptible to. So this was for the overall design at the bottom. And here what you can see is that there is a very large effect of the different cases. So this is in the horizontal mode converted to the construction mode. You can see that there's a very large effect because of the different shapes, and that would be very difficult to pick up if you didn't use this method. Okay, and so my final case I'll talk about is a very unusual metro station in Riyadh. So this is probably how do you put this? This example really emphasizes the utility of using a 3D printed method along with all the pressure sensors, so that we can capture these really intricate architectural designs. So this is in Riyadh, as I said. So you can see our wind tunnel model here. This is the rendering, and these are some of the construction photos. I should check actually to see if it's been completed a bit more. But you can see underneath this that there's a very complicated steel frame, and it twists around to try and get this right effect. And then there's glass in the whole thing. The other important fact that it's a bit tricky to see here, but it's quite obvious. I mean, it's a train station, and that it's actually open through here, so that the whole model is open. Although the model is open, the areas that we are designing are enclosed. So there's a hole running through it, but the differential the pressures. Each one of these sort of areas is enclosed in itself. It's a bit hard to, hopefully that sort of makes sense. This is almost like its own building with a hole running through the middle. And so that's how we were able to model it. And so we followed the same process again. And so the reason that this was interesting, particularly interesting, was that it did actually have quite a low natural frequency, which wasn't really expected. I mean, you can see here that this has got quite a substantial steel frame underneath it. Yet it did have a low natural frequency for one of the resonant modes of the roof, which is a bit surprising, but nonetheless, that's what it was. And you can see it's also quite well spaced out. In the end, the overall effect of that was quite small, and you can see here that for this roof member here that I picked out, but this is quite representative that there wasn't a significant resonant response. Now, why that was the case is, so it's always a little bit difficult to understand, but it's most likely, just going back to the original design, I can't really see it, but basically, because of the very unusual structure, we think that it really broke up the wind flow. So As opposed to a square building or a rectangular building, which has a long uniform side and quite a strong it can generate quite strong pressures on the top. Once you have a building with a lot of step ins, step outs, and curves like this, it really breaks up the wind flow. And so that has the effect of perhaps causing some local areas of high peak pressure. But when you look at the correlation effect, it really drops off that correlation coefficient. So what you can see is that will then feed onto the wind loads and then probably drop the resonant response. So if, for example, the first mode is the whole roof vibrating up and down, then you would need to get a strong resonant response. You need a whole lot of correlated wind loads over the whole roof. Whereas when you have a structure that looks a little bit like this, then it will break that up. Okay, so that was a little bit quicker than I thought, but anyway, so I've covered the 3 different areas, and so let me know if you have any, or let Nick know if you have any questions.
Okay. Dr. Nicholas, thank you for the interesting presentation. So we are now ready to open the floor for questions. So I would like to invite the participants to type questions in the QA chat space. Namun sebelum itu, I'd like to invite some of the panelists that we have here. Pak Davi, Pak Stevi, jika ada yang ingin bertanya, kami persilahkan, Pak.
Okay. Nicholas, I have one question for you.
Oh, yes.
So in general, what will be the main difference on the wind effect of a long span stadium roof if it's a closed roof or the one with openings on top?
Yeah. Okay. Yes. Yes. That's a very good question. Okay. So, let's say, okay. So I've still got this stadium on the screen. So this is the new Jakarta stadium.
Okay.
Right. So it's quite relevant. And so this particular stadium, in fact, has a moving roof. So for this stadium, we actually modeled it open and closed. So what happens is that the closed roof example is probably easier to predict. So a closed roof is a dome, and they tend to, there are codes available, and the dome roof tends to, the word is scale correctly. But to explain that, I'll just contrast that with what happens with a non-closed roof, because there is a complication with a non-closed roof. I'm just going to see if I can find one for you. Where was it gone? Okay, let me find one here, and I'll try and show you what happens. Okay, so what have we got? Okay, this isn't the greatest example. So typically when you have an open roof, like this size here, you wouldn't expect a lot of effect from this part of the roof on the other part of the roof. However, if you have a case where the gap, say this went out a third of the way and there was a third and there was a third, what happens is that the wind hits this here and it generates a lot of turbulence. And then that turbulence hits the leading edge of the other, it hits the leading edge here. Sorry, I'll just put this thing back on. Yeah, just, this might be, yeah. The turbulence hits this leading edge. And so what you can find, depending on the ratio of the height of the building to like the separate, the gap between them, this is quite hard to predict. You get a lot of extra turbulence in there and you get a very large fluctuating load on this lip. And it's actually when the wind comes the other way, when it comes across the stadium. But this is a round stadium, right? But we did one I was thinking about in Turkey, which is an oval. And what happened was that when the wind came along the long axis, there was a lot more turbulence for some reason, and you got a lot of excitation. But when it came across a short axis, it didn't occur, right? Because it had something to do with the height of the stadium roof and the distance from this edge to this edge here. So this is the complication with designing these roofs. It's that you have that extra interference effect. Whereas when you have the closed roofs, you can treat them more like a standard like enclosed building. Well, it is a standard enclosed building. So that makes it a little bit easier. And I think that if you're also how do you put this? So typically what you find is that when people have the open roof here, they tend to have more superstructure on the top. And so people are always ask you about what's the drag load on the superstructure, whereas in the enclosed roof, everybody tries to normally hide it on the inside. Although not everybody does that, but quite often it's hidden on the inside and you don't have to worry about that. So I guess they're probably the couple of differences between the two cases.
Okay, let me continue with that subject. Based on your experience with the wind tunnel test, what would be the size effect of that hole, which will start to play a big role in the overall behavior?
Okay, so going back to the Jakarta Stadium case here, so when you have the hole, so this hole affects the internal, it's probably the effect on the internal pressures, which have the biggest effect. But if you're saying, when do you need to start worried about the hole? It's a pretty tricky question. I think it's the bigger the hole, probably a less effect. Yeah, it's a bit tricky to know with that. Like if you have a very small hole, then the effect is going to be more on the internal pressure than on the flow structure thing I mentioned. Whereas when you have a very large hole, the internal pressures tend to even themselves out more. Yeah, but you might have that extra fluctuating effect. I mean, having said that, you do have to be a little bit unlucky to get that effect where one side of the stadium hits the other. It doesn't always occur. Yeah.
Okay.
So, yeah.
Okay. Thank you for that explanation. Thank you.
Terima kasih Pak Davi atas pertanyaannya. Dari panelis mungkin Pak Stevi, Pak, ada pertanyaan, Pak? Masih di mute, Pak.
Sementara nggak ada.
Oke, baik. Terima kasih, Pak. Okay, I actually see there's question here on the Q&A chat space. Let me just try to read it to you, Dr. Nicholas.
Okay.
So first question by Pak Usman Hassan. Could we use LRC to replace code requirement, or do we have to calculate both and took the conservative one? And I think another question still by Pak Usman Hasman, also related, I think. When we do wind tunnel tests for a long span roof structure, do we have to do it? How many wind directions are we supposed to consider? For instance, do we need to check every 10 degrees or so?
I'll do the first part. So second part first. So typically we would test 36 wind directions every 10 degrees. And so it's on a turntable. So, but I mean, the time-consuming part in making one of these models is making the model and instrumenting it. Whether you do 24 wind directions, which some people do, or 36 wind directions, it's a small amount of time compared to how long it takes to do this. So we typically would do 10 wind directions. Like sometimes people want more, or sometimes people want less, and you can accommodate that. But I would say the standard would be between 24 and 36 wind directions. In terms of the first part, it really depends where you are in the world. For stadiums that we've done in Indonesia, as far as I know, people have just used our wind tunnel results, because it's very difficult to use a code estimate on some of these structures. And so because of that, they tend to use the wind tunnel results. Some places, some codes in the world, for example, ASCE and Hong Kong, they require that you can only drop the pressure to 80% of the code requirement. Now the difficulty comes about with that is that, so this building here is actually in Hong Kong, right? So in doing that design, we had to try and estimate a code pressure, but the code covers square buildings. And so you end up basically over designing the building, because we had to treat this like an awning, and it's clearly not an awning. So that is one problem with that requirement. And so I guess the answer is it depends on your local standard, but it's quite common just to use the wind tunnel results, mainly because it's not sort of fair. It's very hard to use the code to come up with a good pressure estimate.
Okay. So you're saying that ASCE also have the same
Yes.
requirement, is it? Where
Yes.
if you use wind tunnel test,
so for buildings, so when we do buildings in the US, yes, that they have a requirement that the pressures can't be less than 80% of the pressures, and I think the same for the overall loads. They have a few other clauses in there. I think if you do some other testing, you might be able to go to 70%. But yeah, there's definitely that 80% rule. And as I said, it's not too much of a problem. But even some buildings like that aren't square, that are slightly curved, or have, so a lot of buildings have a lot of step ins and step outs because they don't want to just build a square box. It can be quite tricky to try and come up with a fair code estimate. Yeah. And then the other thing, if I'm not sure if you've worked in the US, but sometimes you have the check engineer, the peer review engineer, and then they don't like what you've done too. So. Yeah.
Okay, yeah. So I mean, that can be problematic, right?
Yes. Yeah.
So
yes, that's right.
How would you go about getting a fair estimate of code values if you're in this situation? I mean, are we just allowed to waive the 80% requirement for wind loading, or I mean, how would we try to address the code requirement for that?
Okay. Well, with the US situation where it's strictly, and in Hong Kong where it can be strictly enforced, you have to come to some kind of agreement with the other engineer who's also doing that. So they have an independent engineer, and you have to come to some kind of agreement. Yeah, it's quite difficult. But I mean, normally they're quite happy with the 80% for a normal building. I mean, this airport case is it because it's so unusual, then you end up with very different loads. It's quite tricky. Yeah.
Can you tell us, say how much roughly the difference?
The difference here, I can't remember, but it was, I don't know, it might have been 60% instead of 80% or something. But that's also because you have to use the local code, right? So depending on what the local code says and how you interpret that, you get a larger difference too. But I think some of these were 60 or 50 or 60% of the code. Yeah. But I wouldn't say you'd get that all the time. Because the other thing, like, is that in this particular case, you can't really see it in this picture, but there are all these other buildings around it.
Yes.
And that's not included at all. Yeah.
Yes. And now to compare to what you call code law, if the shape is really irregular, how can we compare it with the code provision then?
Well, yeah,
that's anyway, right?
So that's exactly that is the problem, right? I mean, and it's only some places that you get quite particular about this. They're quite strict on this. But as I said, we've done stadiums all places around the world, and I think Hong Kong was the only one that made us do it for a regular shaped building. Some places are a little bit more practical, and they only require that comparison for buildings, you know, not for like the stadiums or the, you know, these unusual structures. Yeah. I mean, there are other. I mean, if you're concerned about safety factors and that, which is very important, there are other ways to build that in by using different load factors or using ultimate design methods, or there are ways to build in that to reduce your risk without having to go to that really sort of extreme method.
Okay.
So Dr. Nicholas, based on your experience with doing testing of these long span structures, when do you think you know, it is long span structures need to be tested through a wind tunnel instead of just using wind design code values? Are there any rule of thumbs, you know, like in terms of span, in terms of other structural properties?
So going back to what we talked about in the beginning here about like the key differences. So it's really there are two sort of ways of thinking about this. There's, are you worried about designing a structure correctly, and are you wanting to save some money in the design, right? So in terms of, am I designing the structure properly, the time to do the wind tunnel test is when you have difficulty trying to really force the code into your shape building. And so this case here, where you're using essentially to design this, they would have used what they call a monospan roof, which is really designed like for a small shelter, like a shade structure or something, and you're using that to design this roof. It was never designed to do this. So when you're trying to push the envelope of the code too far, that's the first reason why you would use it. And that's from, I guess, from a safety point of view. And also, as I mentioned before, if you have an unusual mode shape, or you have something that is a structural response which is like new and different, and that would be something that when the person that designs the code wouldn't be thinking of. So a lot of the time, like I'm involved in the Australian Standards Committee, when we put provisions in the code, we're thinking about like conventional structures, like it's a cantilever, it's a simple roof. We're not thinking about these really complicated things. So that's one reason. In terms of wanting to save yourself some money by reducing the loads, it's, as you said, it's when it starts to get really long. So probably anything over 50 meters, you would probably start to see some benefit. The other thing is that in terms of the benefit is when you have a lot of shielding, the code doesn't take that into account. So that's one area. And the other thing is that typically when you use a code approach, you have to design the whole thing. So how to put this? The codes will give you pressure, like the worst case pressures over the whole structure, whereas in reality, those worst case pressures are most likely just located in a few small areas. So you can probably just increase the strength of your structure in one area, and then the rest of it might be a little bit less. And that's quite a typical result. You have hotspots which match the code values, and then the rest of the structure is a lot less. But yeah, as I said, I mean, like these are 50 meters, you know, that sort of thing. It's when you start to see the benefit of the design. But if you've got any aircraft hangar, you know how big an aircraft hangar is, anything more than that size would be a benefit.
So going back to the discussion on wind design code values, you know that the code have wind design pressures for main wind force resisting system and also for component cladding. Now, when would one be applicable as opposed to the other, especially when we're looking at a design of long-spanning structures such as, you know, a truss system on a roof stadium, something like that.
Yeah, that's right. Yeah. So typically, I mean, all codes have this. They have what I would refer to as the cladding pressure section, and then like the structural load section. So it obviously depends on the exact wording, but typically, what we recommend is that the cladding pressures for the cladding, their connections, the structures which support them, so the purlins typically, and then the connections between the purlin and the next beam. So they're the four things. But really, it's the main cladding element and the purlin is designed using the cladding pressure, and then the other stuff, everything below that is the main wind resisting frame. Is normally how we would split it up. I mean, having said that, if sometimes it's really dependent on what, how do you put this? So the thought process behind that is what you're trying to look at is, will the wind load be correlated over that area? So this is why it's done that way. So if you have a beam, for example, that was only supporting a very small section, then perhaps you should use the cladding pressure because it's not being averaged out, if you know what I'm saying. So it's really got to do with what we call the tributary area. But typically what I've explained is the way buildings are built. If you had something unusual, you might have to go one level beyond that.
From Pak Budi Hartono, how do you calculate the effect of tornado, when the wind blows in circular direction? Can this phenomena is simulated in the wind tunnel test?
So conventional wind tunnels don't design for tornadoes. So historically, wind standards around the world haven't included tornadoes. The new ASCE standard will include some provisions for tornadoes, but they're very different. And it's not just the swirling of the wind. There are different pressure coefficients, and there's a whole lot of different analysis that has gone into that ASCE provision for tornadoes. So you do get so you should, in terms of the question about the swirling part, if you measure the wind speed, you do enough measurements from different wind directions, you should be able to pick up all of those effects. The main problem is that it's the strength and the unusual pressure distribution you get caused by the tornado. There is a wind tunnel in Canada at one of the universities that they're trying to simulate these things, but it's huge, and it's mainly to do fundamental research into tornadoes as opposed to testing a building. Yeah, but interestingly, it's only recently that the American standard has decided to increase tornadoes, and as far as I know, it's the only standard that is going to include that.
Okay, Nicholas, I would like to ask one question, but this is regarding high-rise building.
Yep, sure.
Okay, what is your opinion on the problems of the SEG Plaza sensor?
So I'm not sure. I'm not familiar with that. So
sorry. Okay, it's a tall building about what? About 60 stories something, which sway a couple of times.
The one in China.
Yeah.
Right. Yes. Okay. I haven't had a look at this, but I did see an article written by Asim Karim. I'm not sure if you know Asim Karim. And he is the president of the International Wind Engineering Society. He's a professor in the US. And I think he was suggesting that it may have been some kind of effect of the top of the building. I think there's a spire on the top and coming down, which was very interesting because that's completely opposite way we think about it. So we design spires all the time, and I'm pretty sure I've never considered the effect that the thing might vibrate and it would come down. But I mean, beyond that, I haven't really looked at it, but it is very interesting. And I would expect that in a few years' time, there will be a whole raft of people with different papers and analysis trying to explain what's going on. But one point about that is if it does turn out to be what Asim is saying, then I think we'd have to really think about how we design these fancy roof features. Yeah, because I mean, it's, as I said, I mean, the idea that you're going to get a dynamic excitation coming down into the building. And the other point is that, I mean, I don't know what mode that's exciting, but it could be that it's exciting one of the much higher order modes that we typically wouldn't consider. And that's why it's caused such a problem. But as I said, it's quite unusual that if you have a higher order mode. I mean, and another thing that I'm not sure about is I would have thought that there would have been enough inherent damping in a concrete structure, because typically the problem you have with masts, as you know, is that the masts have very low damping, and that's what causes the problem. To have that come down into the building and the typical concrete damping not account for it, it's quite, But having said all of that, if that's what it is, you can put something around the mast to break up the vortices, and they should be able to sort it out. Hopefully.
Thanks. It's an interesting subject.
That's right. Yeah.
For years to come.
Yeah.
Okay.
Okay, we have a question from the participant, Usman Hassan. Dr. Nicholas, do we have to consider crosswind to design long span roof structure, or just principal direction only?
Okay, so the answer to that is kind of. So when people talk about crosswind response in terms of a tall building, what we're talking about is we have a tall building, the wind's coming, say, parallel to the x-axis, and we're having a lot of vibration parallel to the y-axis or perpendicular to the wind flow. In the building, the roof example, if you think about if it's as a building on the side, then one way to think about it is nearly all of the response is actually a crosswind response. It is actually a lot of fluctuation. So that's one way to think about it. But I think what the person's actually asking is more to do with probably unusual wind angles inducing strong responses that aren't in the same direction. That's what they mean by crosswind. I mean, maybe they can ask a follow-up question, but you don't need to explicitly account for a long wind and crosswind, because the wind action is actually, or generally speaking, mainly perpendicular to the flow. I'm not sure that 100% answers their question, but then the only load parallel to the direction of flow would be, in this case, for example, would be the drag on the top. If they're talking about, do they need to worry about the side-to-side force? Typically, you don't need to worry about that, because, as I said, this is more like the building being on its side than the building being that way. Does that kind of answer your question, or maybe they can ask another question?
So maybe you can also talk a little bit about the process involved with regards to coordination between structural engineer and wind consultant if wind tunnel test is used. I mean, what sort of information are required, and what sort of output will be provided?
Sure. So Okay, so to start with, we need to build the model. So we would need some architectural drawings of the model. And so these are the architectural these are based on the architectural drawings. That's the first thing. And then we start the process of building the 3D model. The next step is that we like to look at the structural framing. And the reason we look at the structural frame is if we go forward to this example here, just go forward to this example here, we would try and line the panels up with the structure, something to do with the structural frame. So typically the main beam would be underneath the center of that panel. So I'm assuming this is to scale, I think it is, that these are the main beams and they should sit underneath these panels. And so that's an important step. And at that point, what we would do is we would do this drawing and we would send it back to the structural engineer. We might have a chat with them about exactly how that lines up. And so this happened, this building we were doing in Korea a few months ago, that they had a lot of trouble with this because our panels weren't lining up with their trusses the way they wanted to. It was a little bit all over the place, but because they'd moved their structure. So they sent us a structural drawing, we did the panels, and then they changed the structure. Yeah, so there was that issue there. Then the next step is that if we're going to do the LRC, then we have to go and talk about the influence coefficients. And I went through the influence coefficient method. The most common question we get with the influence coefficients is which load effects to choose. Because I mean, we can do 50 or 60 or 100 load effects. It's not a problem. It's just that it ends up being a lot more, we generate a lot more data that needs to be processed. But that's probably the most important conversation that we have with the designer. And we need to do that with the designer. We can't, like, we can give you some advice on this, but the designer of the structure should understand what the critical connections are, which beams are going to experience the load, what they're most worried about. And so they really need to design and help us to choose those. And at the end of the process, what you will get back is essentially a spreadsheet, and it will give you tabulated values. So each one of these pressures, each one of these panels will have a pressure. So in this case, there's 100 areas, and if there were 40 load effects, we will give you 80 pressure distributions. So that process obviously can be automated, and that's what you would get back. So in terms of the structural engineer, though, one of the most time-consuming parts I understand, and like I haven't done this, is that if we say that you need to put 1 kPa on this lot here, and you've got a series of members under it, depending on how your program works, you need to convert that 1 kPa into UDL on several beams, and you might have to, that could actually be quite an involved process. And so for some complicated structure, it's a combination of UDLs and point loads they have to do. So that is something to be aware of, that it could be quite an involved process from the structural engineer point of view. Yeah.
So using this information, the structural engineer then are able to run their model and determine the internal forces, conduct their design, evaluate the displacement and so forth, right?
Yeah.
So what happens if there's problems with, it's the displacement not exceeding acceptable criteria, things like that? Would there be any maybe suggestions from you, for example, as the wind consultant, to try and improve, I don't know, reduce design pressure, things like that?
Yeah, it depends. Yes, we have done that, but typically, as you know, the architect has designed the outside shape, right? And it can be very difficult to do substantial modifications. So we have done this in the past to try and make small changes if there's small localized areas. But if you have large if you have a major member, then it's likely to be affected by a very large amount of the surface area of the roof. It's unlikely that the architect will change their drawing based on what I tell them to do, right? I mean, and so it's more of a case of having to adjust the structure. Now, if you do make a small adjustment to the structure and it doesn't significantly affect the influence coefficient, then you can do that by yourself. And so people do this quite often. They'll change the joint sizes.
I see.
Right, but if then you say you have to change the beam significantly, and then that results in a large change in the influence coefficient, then we can, as long as the outside form hasn't changed, we can redo the analysis and give you a new set of pressure distributions. But as I said, most of the time it's just changing joints. Okay. Yeah. Or maybe maybe increasing the diameter or something here. But I mean, it's typically it's not a big
Now, I assume you also need dynamic structural properties from.
Yes, that's right. So when we do the resonance analysis, so you need to know so going back to this here, you need to know the mode shape and the mass, the equivalent mass of each panel. So it's if you have this is also can be a little bit time consuming. So if you have a panel that covers, say, these members in here, then you need to include not just the mass of the PTFE, but the mass of the structure immediately below that. And I believe that has also taken people some time because they don't actually have that to hand because it's not part of their normal design process, right? To know what that mass is.
How about damping?
Sorry, and the damping value we would typically use a value of say 0.5%, or if it's if we can do a variation too on that. And that is one other thing in terms of factors of safety and everything, because we only use the structural damping, and typically there would be a little bit of positive aerodynamic damping, especially for a roof structure. So what I mean by that is when the roof moves around, there'll be a bit of extra damping caused by its interacting with the air, and that will actually decrease the resonant load slightly. Now, we don't explicitly account for that, but that's another sort of factor of safety kind of thing.
Okay, thank you.
Okay.
So I see that it seems like we have no further questions yet.
Okay.
So Pak Devi and Pak Stevi, are there any further questions, Pak?
No. Thank you for the presentation. Great fun. We enjoyed that and we learned a lot from you, Nicholas.
Well, thank you for inviting us to talk to you.
Okay.
Okay. Well, if you have any other questions, I guess you can let you know and I can answer them later.
Thank you very much.
Okay.
So, Bapak Ibu, mungkin kita bisa akhiri acara webinar kita. Let us thank Dr. Nicholas for his time and his knowledge sharing. Dr. Nicholas, do you have any closing remarks you would like to say?
No, other than thank you for inviting us, and I hope you found it interesting, and you know where we are if you have any other questions. And I'd like to say that we have done over the years quite a bit of work in Indonesia, and I've been to Jakarta and enjoyed the work and the interaction and some very interesting stadiums that we have done, certainly in the area. Very good.
Okay, thank you. Thanks. Bapak Ibu sekalian yang saya hormati,